In this video, we discuss finding the area of a region bounded by a polar graph, so a region that looks like this. Finding the integral representing this area really comes down to understanding how to find the area of a circular sector. So if this is a circle, let's just say it's a circle of radius r, and I want the area of this piece where this is the angle theta. That's just going to be a fraction of the total area of that circle. So the total area of the circle, we all know, is pi r squared. And then I just have some fraction of that area. Well, the right fraction comes from taking that angle theta and dividing by the largest possible angle. So it's theta out of 2 pi. So when I simplify that, the pi's reduce, and I end up with 1/2 of r squared times theta. So the area of this little circular sector is 1/2 of the radius squared times theta. Well, in the same way, if I want to find the area of a region like this, so I've got r equals r of theta here. R is continuous. It's not negative. And we're on the interval from alpha to beta. And if I subtract alpha from beta, I get some angle between 0 and 2 pi. So that's less than 2 pi radians. Then the area can be found, the area of this can be found by taking this interval from alpha to beta and separating it into a bunch of little pieces. So let's say we take it and we subdivide it into n pieces. Here, n's going to be pretty small. Looks like n is going to be 4. And then on each subinterval, we evaluate r of theta, and we create a little circular sector. So you pick a point, and then you evaluate. You pick a point, and then you evaluate. And then you find the area of each of those little pieces, and you add them together. Well, if this angle is delta theta, then the area of one of those pieces is, we could call it delta A, is 1/2 of that r of theta quantity squared times that angle, which is delta theta. And if I want the total area, I just add those up. I have this area plus this area plus this area plus that area, and that's going to be approximately equal to the area of the yellow region right there. If there are n little pieces, we'll sum as I goes from 1 to n. And if I want the exact area, I want to take the limit as the number of pieces goes to infinity. This is where delta theta is beta minus alpha. It's just a finite number divided by n. So as n goes to infinity, delta theta will go to 0. And we end up with this. We have 1/2 of r of theta squared. That's r as a function of theta squared. We'll integrate with respect to theta, and we'll integrate from theta equals alpha to theta equals beta. So that's the area of this. It looks pretty simple, but there are a couple of requirements. So that's our formula that we'll use. So this is the area provided the following is true. R equals r of theta must be continuous and must have the same sign. So it must be non-negative. So either positive or 0 on the interval from alpha to beta, or non-positive So it can be negative and sometimes 0, but not positive on the interval from alpha to beta. But it can't change signs. If r of theta goes from positive to negative, this may not work. Okay. But if r is continuous and non-negative, or continuous and non-positive, then the area of something that looks like this can be found this way. So let's do an example. Let's say you're given that r is equal to 3 times, or sorry, I wrote 3. I said 3 and I wrote 4. 4 times sine of 3 theta. This is a rose curve. Let's say somebody asks you to find the area of one petal of this rose curve. Well, the first thing you want to do is graph it. And you want to be very conscious of where you're starting a petal and where you're ending a petal. So if we want to graph this rose curve, the first thing I would do is graph r as a function of theta. So here's r versus theta. The amplitude of my sine function is 4, so we go from -4 to 4. The period is 2 pi over 3, or we could call that 4 pi over 6. And all the interesting things happen at 1/4 of the period. So this is pi over 6, this is 2 pi over 6, this is 3 pi over 6, and that's 4 pi over 6. I know all of those, well, 3 out of 4 of those simplify, but we don't want to leave it simplified. I think I'd rather leave it this way. So we graph that. And then we use this graph to create our table of values. And I like my increment of theta to be 1/8 of the period. And in this case, I've got 1/8 of 2 pi over 3. Ends up being pi over 12 or 15 degrees. We graphed this one already once before. So we'll use 0 degrees, 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, 90 degrees, and so on. I think we've got one petal in there. 105 degrees, 120. And then we said, okay, not at the eighths, but at the fourths, at 0, 30, 60, 90, and 120. I'm going to be at 0, the max, 0, the min, and back at 0. So when theta is 0, we get sine of 0, which is 0. And then at 30, that's sine of 90, which is 1. So we go 0, 4, 0, -4, 0. And then these values, at 15 degrees, this is going to be sine of 45 degrees. So we'll have sine of square root of 2, or sine of 45, which is square root of 2 over 2. So we got 2 root 2. And I'm doing this so quickly because we've done it before. That's also 2 root 2. Down here by symmetry, that's -2 root 2. And then over here, we also have -2 root 2. Okay. So we drew this graph, we found the increment, and then we made this table of values. And now we're going to use this table of values to graph at least one of the petals of this rose curve. So I've got my table over here. Pretty much always need to graph before we find area. And we start at 0, 0. And then at 15 degrees, we go out 2.8 units from the origin. I'm going to say that this is 1, that's 2. Oops, that's on the 30-degree line, not the 15-degree line. This is 1, that's 2, and that's 3. So we want to be at 2.8. So approximately right there, okay? And then at 30 degrees, we want to go out 4 units. That's 1, 2, 3, and 4. And then at 45 degrees, we want to go out 2.8 units. So on the 45-degree line, we go out 2.8 again. And then at 60, we're back at 0. So that's one petal. And there are more of them, but I only want one. And that whole petal was traced out as R went from 0 to 60 degrees. So in radians, that's 0 to pi over 3 radians. We got one petal. Okay, so let's find the area of that petal using our formula. Okay, so according to our formula that we just derived, we'll have the integral from 0 to pi over 3, that angle to that angle, of 1/2 of r of theta squared with respect to theta. We're integrating 1/2 of r of theta squared with respect to theta over this interval. Well, r is given by 4 sine of 3 theta. So you want to square the 4 and square that sine function. 4 squared is 16, half of 16 is 8, so we can pull out the 8. And then I've got sine of 3 theta, quantity squared. And remember, we need this function to be the same SIG and sine the whole time, and it looks like it is. All those R values are positive. We also saw all of those R values were positive as we were graphing these. Now, if I've got sine squared of some angle, I need to use a power reducing formula to evaluate this integral. Can't do a u sub because there's not a cosine of 3 theta anywhere. So I have to replace sine with 1/2 of 1 minus cosine of double the angle. We take 3 theta and we double it, so it's going to make that 6 theta. And that's what we have right there. 8 times 1/2 is 4. You have the integral from 0 to pi over 3 of 1 minus cosine of 6 theta d theta. And now we antidifferentiate. The antiderivative of 1 with respect to theta is theta. Antiderivative of cosine with respect to theta is sine of the same angle. Since there's a 6 inside, we have to divide by 6. If that's a k, we always divide by k. And evaluate from 0 to pi over 6, or pi over 3, excuse me. So you have 4 times pi over 3 minus 1/6 of sine of 6 times pi over 3. So that's 2 pi minus 4 times 0 minus 1/6 sine of 0. So we end up with 4 pi over 3. And that's it. Okay, so that's a sine of, or the area of one petal. Now in the next video, we'll look at the area between two polar graphs, which is a little bit more involved.